of the is online some theory. So today I want to solve some examples. So the first example, so we want to find the matrix rho for the canonical ensemble. And the H here is the Hamiltonian. So the first example I will start to talk about is the electron in external uniform magnetic field. So we consider a magnetic field in the z direction. So B is B law, and we just send it one electron as a particle to inside this external magnetic field. So the classical picture is that the electron started to move like a proton, but in opposite direction. It started to move. The classical picture is that it started to move in the helical path. So, like that, but in opposite direction to the proton, but the same frequency and the same pitch length. So, same frequency. Frequency will be EB over M. This is a classical picture. In quantum mechanical picture, the picture is different. We consider the electron as a particle which it gains some potential energy. So the potential energy which gained by the electron is minus mu dot B. So the mu is called the magnetic moment. B is the external magnet. The theory to find the mu is it's out, is beyond our talk, but actually we can show that the mu is mu0 multiplied to the things which we call it matrix mu. What is the sigma? Sigma is the vector which is related to the spin. Spin of the electron is given by the h squared over 2 sigma. And sigma is a matrix vector. So the component of the vector are considered as a matrix. The component of the vector are matrix. And you know that this sigma, they are called Pauli matrix. And you can circulate that sigma x, sigma y, sigma z. So they have a structure called SU2 group. So, and then in the Z representations, I mean, if you consider the Z as a diagonal element matrix, this sigma Z is given by the two-dimensional matrix, and by this way, sigma X will be 0, 1, 1, 0, and sigma Z will be 1, 0, 0, minus 1. I rated that, so sigma y. Sigma y will be 0i minus I. So this is the the form for the matrix. But this is a one representation. If you change it your basis, I mean, if you want to write the matrix in the form that the sigma x be diagonal, so the form of the sigma z and sigma y will be changing. But we write in the z representation. This is the z representation of our matrix form. So this mu b is magnet moment of the electron is E h bar. So we didn't write that, but this is actually related to the h and the Planck, the Dirac constant, and it's related to another parameter like the mass of the electron and the velocity of the light. But we keep it just as the constant, so this is the constant actually. And this is related to the h bar and the mass and the velocity of the light and these things. I don't want to add more quantum mechanics here. So this is the potential energy. Actually, by the magnet, by the electron in the external magnetic field, we consider the Hamiltonian. Hamiltonian should be the kinetic term plus the potential term, mu dot p. But in the very good approximation, we just consider the potential term and we ignored the kinetic term. So potential term is the important term here. So added one vector here at the mu, so this will be the term. So let's start to write the Hamiltonian h minus mu b sigma dot b will be minus mu b, b sigma is z. Yes? This is sigma y, it should be minus I here, minus I, not I. So the challenge now is that to write the expression of the minus beta h. Expression of the beta mu b b sigma z. So you see that what is happened here, what is appear here is just a constant. We can call it alpha or anything. Yes? So your challenge is to write expression of the alpha to the matrix. What is that expression of the exponential alpha sigma z? If you forget about the structure of what is written here, you can write this formally, you can write it that. No? Yes? And look at that. I will divide this to the three parts when I write the even plus odd. Huh? I started from 1 and 3, 0 to 4. Huh? Okay. What is the even? Even means that the n should be 2n here. So sigma here, I can start from 0 to infinity. Alpha sigma z 2n factorial. Plus, and here I can start from 1 and just write alpha sigma z plus 2n plus 1, start from 0. Plus 2n plus 1 factorial. So look at that. What you needed is, you needed to know what is the sigma z square power n. This is your, and what you needed to know is that also you needed to know that what's the power of the sigma z when the sigma z is odd. So look at that. That will be sigma z power 2n multiplied to sigma z. So what I needed is the sigma z squared, or sigma z squared power 2n. I needed to know that what is the even power of the sigma z. Huh? This is the sigma z. This is the sigma z. So I needed to calculate sigma z squared, sigma z 4, 6, the even powers of the sigma z. No? I needed to know what is the sigma z power 12. That's the sigma z, 1, 0, 0, minus 1. So immediately you get sigma z squared is just 1, 0, 0, 1, 0, 0, minus 1. So if you calculated that, will be 0, 0, 0, 1. This is the unit matrix. No? So what is the cubic power? Cubic power will be just square power multiplied with that. No? And this is the 1, so it will be sigma z. Do you need to do more calculation? No. Because sigma z square is 1, sigma z power 4 is 1, power 6 is 1, power 8 is 1, so everything is 1. So this is what is written here, is just unit matrix. Okay. Just by resulting that here, you will get 1. This is this is a matrix 1 actually. Sigma n 0 to infinity, alpha power 2n factorial, plus sigma z and sigma a okay. Look at that. Do you remember what's the equivalent expression for that sigma n 0 to infinity? Which kind of the function have this kind of the Taylor series?
Exponential.
Cosinus hyperbolic, huh? Cosinus hyperbolic. This is the cosinus hyperbolic alpha. And what's that? Sinus hyperbolic alpha. So the exponential minus beta h is just matrix of 1 multiplied to cosinus of hyperbolic alpha. I know that what's the alpha, I defined it. This is that. 1, 0, 0, minus 1 sinus of hyperbolic alpha. I don't think that you needed to more algebra because it's easy just to combine these two together. And what is the cosinus plus sinus? Is exponential. Huh? Is exponential 0, 0, and this is also yeah. This will be exponential of the minus. Yes. Okay. That's all. So you find the exponential of the matrix, and this is what you needed here. And you need also the trace of this matrix. Huh? Trace exponential minus beta h is just the summation of the elements in the diagonal part, e alpha plus e minus alpha. 2 cosinus hyperbolic alpha. That's all. So we find the row. So we find the row. This is the row. So this is the row matrix, or the form of the row using the von Neumann theory. So this question cannot be solved by the method of the previous chapters, except that you find the eigenvalue of the Hamiltonian, or if you define the phase space around this theta is the angle between the B and sigma. So this is the tracer. So the matrix row is just 1 over 2 cosinus hyperbolic alpha B alpha 0, 0. By that you can define everything, like you can define the average of the magnetic moment, mu z. What is the mu z? Is mu b sigma z. What is the average? The average of everything was just multiply this expression to the rho over trace rho. Yeah? So when we trace mu b, this matrix, multiply to this matrix over trace this matrix. And that's not difficult to calculate, just you needed to multiply these two matrices. If you multiply these two matrices with E alpha, 0, 0, minus E alpha, and here you, what is that here? Trace E alpha, 0, 0, E minus. And look at that, what we find. What is the trace of this? E alpha, E minus alpha. E alpha minus. Mu b, cosinus hyperbolic alpha, sinus hyperbolic. Mu b cotangente hyperbolic alpha. Mu b cotangente hyperbolic. Mu b beta. What is the beta? kbt. This is the average of the magnetic moment. That was the magnetic field. Yes. And that is the vector mu. So this is the theta. So the theta can have any value. Any value. If you make the average of this vector, the average of this vector will be this quantity. This is very important, because how you can estimate that what is the average of the vector when there is a parameter and this parameter change. This is the average of this vector mu at the each finite temperature T. So if you have a question about this calculation, you can ask me.
Vector, isn't it the opposite in the denominator? E alpha, isn't it minus e to the power minus alpha and then below plus? Because of the matrix?
Yes, you are right. Here will be minus, yes. Here will be positive, yes. So will be sinus. That's right. Sinus and the cosinus will be here. So that will be tangent, tangent. That's right, yes. That will be tangent hyperbolic. So tangent hyperbolic of this is given the average of this vector called magnetic moment. So you can solve this problem by the method of the chapter of the canonical answer. But I can find the same expression by that method. But I just give you the task if you want to do that. So using phase space method, also you can do that. What you needed is you again write the Hamiltonian, so Hamiltonian will be the same. Instead of that, we needed to use the classical method. So mu dot b is just mu b cosinus theta. And theta is the angle between 0 to p. Yes? This is a classical method, not Feynman method. In classical method, do you remember what you needed was the partition functions? The partition function for the one electron was, you remember what was that? Sigma e minus beta e, sigma over e. Or if you want to make it this classical, you can write it that 1 over h bar integral d p theta d theta E minus beta, H theta and the P theta. And here you can keep it also the kinetic term, no problem, but it will be eliminated finally when you get when you calculate the average. This kinetic term doesn't have any contribution to the average of this vector. Okay, this is just starting. So do this. Just make it this integral. You will find the sum partition function. From that, you can find the expectation value. But I don't do that because it's very far from our chapter. Anyway, that was one of the questions in the end of the chapter. I think that was explicitly a question in the